Hello everyone, my name is Yuvraj Didwal, and this is my lab report for Lab 5, the Slinky Drop, and this is Physics 2211. All right, getting started. The introduction of this lab. The purpose of this lab is to figure out why the bottom of the Slinky remains stationary even while the object is in freefall until the top of the Slinky has fully collapsed. The secondary purpose is to conduct a physics experiment of our choice, to follow our physics passions and just pursue something that we're interested in. All right, so some fundamental physics principles in this experiment. We've got the gravitational force, which is the force is equal to negative mass times the gravity constant, which is negative 9.8. We've also got the drag force, which is force equal to negative the drag constant times velocity. We've also got Newton's second law, also known as the momentum principle, which is the net force is equal to mass times acceleration, or the net force is equal to change in momentum divided by the change in time. We've also got the velocity update and position update formulas, which, frankly, if you have not memorized by now, is kind of embarrassing. But the final velocity is equal to initial velocity plus the net force divided by mass times time. We've also got the position update formula, which is the final position is equal to initial position plus the average velocity times time. In our experiment, we got our system, which is the spring, and our surroundings, which is the earth. So this experiment is quite simple. All you have is a Slinky that you hold at the top as you extend down as it reaches static equilibrium, and then you drop it from the top, and as it drops, the bottom of the Slinky stays stationary until the top of the Slinky hits it, and then they both fall at the same rate down. As you can see from the tracker data, you can see that at the start, the bottom of the Slinky remains stationary until about 4 seconds of the slow-mo video, and then after that, it goes down along with the top of the Slinky. And this is in the slow-mo video, not in real life. So some initial conditions. We've got the mass of the Slinky is about 1.8 kilograms, and this is just taken from a little bit of guess and check. We got position vector, which is approximately 0, which is taken from tracker, and our initial velocity, which is equal to 0 because the object starts at rest. So this experiment can be chalked up to 2 separate sections. The first section is where the bottom of the Slinky remains stationary due to the net tension force equaling the net weight force, setting the net force equal to 0. And we've also got the second section, which is where there is no longer a tension force and there's only a drag force pointing up, acting against the weight force. In this case, in the first case, the tension force is equal and opposite to the weight force, so the object remains stationary. However, in the second case, the drag force is not equal to the weight force, so therefore the object does start falling down. And in both these cases, we got our ball velocity update formula and our ball position update formula. All right, as you can see here, we have graphed out the observed positions of the bottom of the Slinky and the modeled positions of the Slinky. And this is over a time of 7 seconds. This is the slow-mo video, not the actual function, because it's just easier to figure out the points in the slow-mo video. As you can see here, this is all nearly the same graphs. There is some slight differences, and we'll discuss that in the conclusion slide. All right, so some conclusions. During the first part of this experiment, the bottom of the Slinky had a tension force that was equal and opposite to the force of gravity. However, when the top of the Slinky came down, there was no longer a tension force holding up the bottom of the Slinky, so it started falling as shown as in the model and in the video. In the last slide, we saw there were some discrepancies in the data, but those can be chalked up to outside forces acting on the system that were not accounted for in the model, or in human errors in tracker or in the experiment itself that messed up the model a little bit. Anyways, thank you all for listening. This is Yuvraj Didwal, Lab 5, and I'll see you guys in Physics 2212 next semester.